In our last chapter, we talked about ionic bonding, a situation in which you have a cation that gives up electrons to an anion that takes those electrons, and then as a result, those two charged particles get together to form a compound. That's great for things like metals and nonmetals, but what happens, say, when you have elements, nonmetals for instance, that don't like to give up electrons? How do those elements come together to make compounds? In this chapter, we'll talk about just how that happens. So let's get going. Remember, the whole reason why these atoms get together in the first place is because each of them want to have 8 valence electrons. We call that the octet rule, remember? In the case of ionic compounds, we discussed how metals will give up electrons to do just that, and how nonmetals will take electrons to fill their outer shell. But what about compounds like water, or methane, or any compound that's composed of nonmetals entirely? How do those atoms get together to form that compound? Well, if it's not an ionic compound, those atoms get together by means of covalent bonding. A covalent bond is formed when atoms share valence electrons. By the way, compounds that are formed by means of covalent bonding are called molecules. So the very definition of a molecule implies that there are covalent bonds involved in that compound. So, 2 or more atoms can combine covalently to form a molecule, and the majority of covalent bonds occur between non-metallic atoms. Things like carbon, oxygen, nitrogen, and so forth. What happens when atoms share electrons? How does that work? So as 2 atoms approach each other, there are several different forces that are happening. A couple sets of repulsive forces, the repulsive force between the electrons of one atom and the electrons of the other atom, for instance. You also have the repulsive forces between the nucleus of one atom and the nucleus of the other atom. But you also have attractive forces between the nucleus of one atom to the electrons of the other atom, and vice versa. So as those atoms move closer, there's a balance that occurs between the attractive forces and the repulsive forces. And at a certain point, you get a maximum net attraction that's achieved. So this stable arrangement occurs when there's some optimal distance between the nuclei of each atom. And at that point, the net attraction is greater than the net repulsion, covalent bonds. You could think of it as electron density of one atom kind of overlapping with the electron density of the other atom. So if we're talking about a single covalent bond, that single covalent bond consists of one pair of electrons. So the density of one atom is overlapping with another atom in such a way so that both of them have 2 electrons worth of density between them. That's a single covalent bond. Let's take 2 fluorine atoms, for example. Each fluorine atom has 7 valence electrons, right? So it only needs 1 more electron to fill that outer shell, that outer valence. If fluorine 1 overlaps that single electron with fluorine 2's single electron, do you see what happens? They now share a pair of electrons between them. That's one covalent bond. So the electron densities of these 2 atoms are overlapping in such a way such that there are 2 electrons worth of density between them. Get it? And by the way, we share by the pair. They don't share just 1 electron between them, it's always going to be 2. And it's kind of hard for us to think in terms of electron density and clouds overlapping. We need something a little more tangible. To do this, we use the electron dot structures that we used back in chapter 5. Remember that? Fluorine 1 would have 7 dots around it because of 7 valence electrons, and fluorine 2 would have 7 dots around it as well. And when we put them together, we can show a bond has occurred by having the 2 dots between the atoms. But you'll notice that some electrons are involved in bonding and other electrons aren't. We can have what are known as bonding pairs, in other words, a pair of electrons involved in bonding, or we can have non-bonding pairs, pairs of electrons that just sit on the atom and aren't being used in a bonding situation. In this fluorine molecule, right, we can see that the 2 fluorines are sharing a pair of electrons, and each fluorine has 3 additional non-bonding pairs. Each fluorine, therefore, has a total of 8 electrons surrounding it, thus fulfilling the octet rule for each fluorine. This use of electron dot structures to show the electron configuration in a molecule is called a Lewis structure. In the Lewis structure of the fluorine molecule, we can show it this way, or we can show it this way. using a dash to indicate a bonded pair of electrons. And I'll be honest, I like this way a little bit better because it differentiates between bonding electrons and non-bonding electrons. We could draw the Lewis structure of the hydrogen molecule, where one hydrogen bonds with another hydrogen, forming a single covalent bond in between. Mind you, 2 electrons is all each hydrogen can handle, so they're perfectly happy with that one covalent bond between them. That's all they need. The Lewis structure of the hydrogen molecule then looks like this. Very simple, huh? Hydrogen can only form one covalent bond. That's all it can do. 2 electrons total is all each hydrogen can handle. Fluorine can only form a single covalent bond with another atom because it only needs 1 electron to fill its outer shell. And most of the time we're going to see that the halogens, group 17, form 1 covalent bond each because they only need 1 electron. Although I will tell you that the bigger halogens can actually form more bonds, but we'll get to that later. Now some atoms need more than 1 covalent bond in order to achieve that 8 valence shell that they want. Oxygen or other group 16 elements, for example. Oxygen has 6 valence electrons, so it's going to need to share 2 more times in order to have a total of 8 valence electrons, isn't it? Now it is possible for one oxygen to share twice with another oxygen. That would be what we call a double covalent bond. In this case, what we're saying is that there's enough electron density between those 2 oxygens that equals 4 electrons worth of charge. By showing 2 dashes between those oxygens, we are showing that there are 2 pairs of electrons, or a total of 4 electrons between the 2. Each oxygen then will have 2 more unbonded pairs of electrons, right? So each oxygen will now have a total of 8 electrons surrounding them. Do you see that? The 2 unbonded pairs on each oxygen, and then the 2 pairs in the middle. Remember that each oxygen has access to those 2 pairs. So that's an example of a double covalent bond, in which there are a total of 4 electrons between the 2 atoms. Oxygen, though, can do more than just make double bonds. It could do 2 single bonds with 2 other atoms. In whatever combination, oxygen just needs to have 2 covalent bonds in order to be filled. Water, for example, is a molecule in which you have an oxygen that has 2 single covalent bonds with 2 separate hydrogen atoms. As a matter of fact, other group 16 elements can do this as well. Do I hear 3? As a matter of fact, yes. Let's look at nitrogen. Nitrogen has 5 valence electrons, doesn't it? Let's see what happens then when we take one nitrogen atom and pair it with another nitrogen atom. In order for each nitrogen to have a total of 8 valence electrons, it will have to share 3 times. So that's exactly what they do. The one nitrogen will share 3 times with the other nitrogen and form 3 covalent bonds for a total of 6 electrons worth of density. Showing this in Lewis structure form, we simply have 3 lines, 3 dashes between the 2 nitrogen atoms, and then each nitrogen will have an unshared pair of electrons as well. In this configuration, each nitrogen has access now to 8 valence electrons. Each nitrogen has the unshared pair and access to the 3 pairs in the middle. But just as we said with oxygen, nitrogen doesn't have to make a triple bond every time. It could make 3 single bonds, or a double and a single, whatever combination it needs to make in order to have 3 total bonds. And by the way, this goes for group 15 in general. Here's the ammonia molecule. You can see that in the ammonia molecule, nitrogen has 3 single covalent bonds with 3 different hydrogen atoms. Then it has a leftover pair of unbonded electrons. Group 14 elements like carbon tend to form 4 total covalent bonds. You can form a combination of 4 single covalent bonds or 2 double covalent bonds. I just mean that it has to be a combination that totals 4. Why? Because they have 4 valence electrons, which means they need to share 4 more times to have a total of 8. Whatever combination it needs to make in order to have a total of 4 bonds. Here's a molecule called methane. You can see that there's a carbon in the middle of the molecule with 4 hydrogen atoms on the outside. The carbon forms a single bond with each hydrogen atom. That's a total of 4 bonds, isn't it? And you'll notice that after sharing, the carbon now has a total of 8 valence electrons available to it. And of course, each hydrogen is full by having its 2 valence electrons each. By the way, in order to make that stable configuration, many of these elements will hang out in pairs. We've alluded to a few of them. Hydrogen will form what we call a diatomic molecule, a 2-atom molecule, get it? H2. Or O2, oxygen will form a diatomic molecule as well as nitrogen and fluorine. All of these will form what we call diatomic molecules in order to have that stability, that total of 8 valence electrons. If you're wondering which ones form diatomic molecules, there's a number of different mnemonics that we can use, or memory aids. You could arrange the elements so that they say Honkelfibber, or maybe Brinkelhoff. I don't know. I have no bright or clever friends. That's kind of harsh. Don't use that one. Or you could use the ever popular have no fear of ice cold beverages. A single covalent bond is also called a sigma bond. Now, you could think of this as a straightforward bond. How about that? Sigma, straightforward. In a sigma bond, the electrons that are being shared are centered between the 2 atoms involved. So when you have 2 atomic orbitals that share end to end like so, it concentrates the electrons in the bonding orbital between the 2 atoms. Sigma bonds can form when 2 s orbitals overlap, or an s orbital overlaps with a p orbital, or 2 p orbitals overlap, but it has to be an end-to-end overlap. Water has 2 sigma bonds, the bonds between the oxygen and the 2 hydrogen atoms. Methane has 4 sigma bonds. The orbitals in the carbon overlap end-to-end with the hydrogen orbitals forming sigma bonds. Well, let's say you have multiple covalent bonds between 2 atoms. Here I have 2 atoms with their p orbitals represented. Notice I can only get one set of p orbitals to overlap end to end, right? How will the yellow orbitals overlap? Or how will the blue orbitals overlap? They can't do it end to end. So they have to form what's called a pi bond, or a parallel overlap. So therefore, in a multiple bond situation, you'll have a sigma bond that forms with the 2 end-to-end orbitals, and the orbitals that can't overlap end to end will overlap in parallel fashion, like this. Since the blue and yellow orbitals can't overlap end to end, they have to do the next best thing. They overlap in parallel fashion. Remember, there was a blue on top and blue on bottom on this atom, and a blue on top and a blue on bottom on this atom? So the tops overlap together respectively, and the bottoms overlap together respectively, to form what we call a pi bond. And the same goes for the yellow orbitals. Remember, we had yellow on top here, yellow on bottom here, and yellow on top here, and yellow on bottom here. They have to overlap in parallel fashion to form another pi bond. It's important to note that each of those pi bonds only represents 2 electrons. Not 2 on top and 2 on bottom, 2 combined. So the yellow pi bond is top and bottom and only represents 2 electrons. The same goes with the blue. The blue pi bond only represents 2 electrons as well. In other words, those 2 electrons can be anywhere in that blue region. And then you have this sigma bond in the middle where you've had an end-to-end overlap of orbitals. This represents 2 electrons as well. So 2 electrons here, 2 electrons here, and 2 electrons here give us a total of 6 electrons. This represents a triple bond. So in a multiple bond situation, you can have no more than 1 sigma bond, since it's only possible to form 1 end-to-end overlap. Any other bonds will have to be pi bonds. A double bond consists of 1 sigma bond and 1 pi bond, and a triple bond consists of 1 sigma bond and 2 pi bonds. It's interesting to note that a sigma bond is stronger than a pi bond. So that end-to-end overlap provides more strength than a parallel overlap does. However, the combination of a sigma bond and a pi bond would be stronger than just 1 sigma bond. A double bond is stronger than a single bond. And for that matter, a triple bond is stronger than a double bond. As far as strength goes then, the single bond is the weakest, the double bond is next strongest, and the triple bond is strongest of all. But what we find is that the more bonds there are between atoms, the closer they are together. To help you remember and to illustrate this, I'm going to use this rubber band. Let's compare one thickness of rubber band, a single bond, to a double thickness. Notice that it's shorter. It's stronger, isn't it? But it's shorter than the single bond was. Single, double. How about triple? A lot stronger, but also shorter, isn't it? So as we can see, the single bond is weakest, but longest, whereas the triple bond is strongest, but shortest. That's all we'll do for this video. Today we introduced the concept of the covalent bond, how it's a means by which atoms can share electron densities in order to achieve that octet that they need. We discussed the idea that each covalent bond is equal to 2 electrons. So a single covalent bond is 2 electrons, a double covalent bond is 4, and a triple covalent bond would equal 6 total electrons. We introduced the concept of Lewis structures and how we can use them to illustrate the electron configuration within a molecule. We identified 7 elements that like to travel in pairs. We call them diatomic molecules. And we spent some time discussing sigma bonds and pi bonds, how sigma bonds overlap in a straightforward or end-to-end way, and a pi bond overlaps in a parallel fashion. In our next video, we'll spend some time naming molecular compounds. So until next time, God bless.